Welcome to our final presentation, in which we explore fine-grained out-of-distribution detection. Next slide, please. OOD detection is a task of identifying when a model is given input that's unlike anything it saw during training. Many existing OOD methods perform well on coarse-grained datasets where there's a large semantic shift between in-distribution and out-of-distribution samples. But these same methods struggle to perform OOD when there's a fine-grained semantic shift between the open and closed sets, such as at the species level. Next slide, please. With this, we'll use the Caltech Birds 2011 dataset as our fine-grained samples. This dataset contains 200 species of birds, where we randomly split 150 classes as our in-distribution and held out 50 classes as our out-of-distribution samples. We explored the performance of different architectures as it impacts OOD, such as ResNet 18, vision transformers, and self-supervised techniques such as DynoVIT. Using these different model architectures, we evaluate many OOD methods leveraged from the Open OOD framework, focusing on open set recognition.
For our baseline results, we hypothesized that these OOD methods would degrade in performance as fine-grained data is more of a challenge, and so our results met our expectations. We can see a degradation performance on fine-grained benchmarks. Our first attempt was to try a couple of data augmentation experiments using some preprocessing methods that alter the images in some ways. And for the first two, SAM and PixMix, these both hurt performance, and we hypothesized it was because either adding a blur or a texture image with PixMix, as you can see an example of these two images, the second being the mix with the texture. We felt that these most likely hurt performance as they introduced noise or disrupted the fine-grained details that are needed, whereas Rand Augment was more neutral with only like minor improvements, as these augmentations were not as severe, so they likely better preserved the subtle details.
After we experimented with changes to the training process, we thought that changing the underlying backbone might also improve our results. So we swapped our ResNet backbone for a vision transformer backbone, and we actually found that the VIT did perform better than the ResNet on the fine-grained benchmark. But what surprised us is that the vision transformer would then perform a worse on the coarse grain benchmark when compared to the vision transformer on the fine grain benchmark. That was a surprising result, and it suggested that the global attention mechanism can help models detect fine-grained and nuanced features, but then there might be certain objects where class identity depends more on local features, which are actually better captured by filters convolving over local regions. Next slide, please. After experimenting with different backbones, we experimented with a self-supervised learning method. So we took some pre-trained weights and we ran a dyno model, a DynoVIT model on against our fine-grained cub benchmark. Even though this was never fine-tuned on our cub benchmark, it actually outperformed our ResNet. That was true for some of the post hoc methods, but it was not true for all of them. So once again, we show that changing the underlying model backbone can improve performance, but it's not a silver bullet. Next slide, please. Overall, we thought that our study corroborated the suggestions of previous work that changing your training procedure and changing your backbone can change your OOD performance, but overall, the choice of the best OOD method is going to depend upon your data, and the specific choice of your post hoc method still greatly impacts your OSR performance. Ours was a high-level study. We assessed many different methods. Future methods might drill down deeper into actually experimenting with different architectures that might help us understand each one of the methods that we studied more deeply. Thank you for listening to our presentation on OSR detection.